Hi. So, as mentioned, this is about remotely cracking Bluetooth-enabled gun safes and verifying the secure implementation of Bluetooth low-energy devices. I'm Austin Fletcher. I'm a lead vulnerability research engineer at 26 Labs. This is Dan Su. He's a senior research engineer at 26. And we both do software and hardware security there. We work on embedded systems security team where we do product security for various IoT and embedded systems. And we also perform fundamental research into security, including hardware side channel analysis. So we're going to be going over a brief introduction of the topic, as well as an overview of Bluetooth low energy security. We'll tell you about how we found these issues in this safe. We have a demonstration, and then we will talk a little bit about how to avoid making these mistakes in your product. So as mentioned, this is about a gun safe. In this case, it's a Vaultec VT20i smart gun safe. We're going to look at some of the poor implementation decisions that they made and hopefully teach you some best practices on how to avoid some of these in your product. So the gun safe is one of Amazon's best-selling gun safes. It has a number of really cool features. It was successfully funded through a crowdfunding campaign, and it's very popular. So popular that one of our coworkers actually purchased one of these safes, and he was talking about it, and we decided, hey, that would be cool to take a look at it. It has Bluetooth functionality, and we thought it would be really neat to try to break into this safe through the Bluetooth functionality without actually needing to know any of the PIN code or anything else required. So we spent a couple of days on it, and this presentation is a result of that work. So the safe, like I said, features Bluetooth, but it also features another couple of ways to access it, including biometrics, in this case, fingerprints. It has some physical buttons on the top, so it allows you to enter a PIN code to open it, as well as taking a key. And it's advertised as being securely designed, which is why we really wanted to try to break it. So why a gun safe? Well, in America, gun ownership is very, very common. Almost a third of all households have a firearm inside of it. And responsible gun owners will typically try to utilize a gun safe to keep it away from their children, things like that. But they still want access to these safes in the event of an emergency, like somebody breaking into their house. So the problem here really is that historically speaking, secure systems like this gun safe, or a bank vault or something would be hard to break into. They would require either specialized tools or knowledge or lots of destructive, noisy processes to break into. And people got really good at designing these secure systems. So one of the things that they do, though, is they make it hard to actually access the system, hard or time consuming. And that's something that consumers don't really like. So to address this, manufacturers started adding functionality like Bluetooth or biometrics, things that allow a user to more easily access their safe or device. In general, adding IoT functionality to a system that historically has never had one before. And this is, of course, increasing the attack surface of the device, which is great for me as an attacker because increasing the attack surface gives me more vectors into your devices. And securing these sorts of access vectors is very difficult. So in other words, we're going to, from breaking into a safe to being something like this, where you are actually drilling or being destructive to get into the safe, into a situation where you have something like a laptop that's just running some code that we wrote, and it's going to just connect via Bluetooth to the safe, and we should see the safe open. And we'll get into how this works, but we're really lowering the barrier to entry here. So we decided to start looking at the IoT communications of this product, as we often do. And we're looking initially for things like eavesdropping or the ability to perform a man-in-the-middle attack, or even just be able to track where these devices are. So in the case for eavesdropping here, we might be able to intercept the PIN code as the user's opening the safe, or possibly replay a valid opening sequence. Or in the case of tracking, maybe we could track if a user moves one of these safes, or maybe even just drive down the street and see who has one in each neighborhood. So we'll talk a little bit about some high-level Bluetooth Low Energy security. So Bluetooth Low Energy is very, very popular. It's in a lot of devices that we all have, phones, fitness trackers, watches, your car. They're cheap to produce products with these things. A lot of commercial system-on chips that you just buy will support Bluetooth off the shelf. And typically when people are developing these products, they're concerned with rapid development and mass market sales. So they're trying to make it cheaply and efficiently. And they're maybe not giving the kind of respect to the security aspect as they should. And we'll see later on that Bluetooth Low Energy has various things that you can do to help secure your product, but a lot of these require additional hardware or have some impacts on battery life that a lot of developers don't really want. And so due to these issues, a lot of devices rely on the least secure possible operational modes with Bluetooth. And security issues are extremely common across these devices. So Bluetooth Low Energy is really a marketing term for like Bluetooth 4. So this is kind of split. There's a number of versions. It's kind of split between 4.2 secure and later, and 4.2 and earlier, which becomes legacy. And so the difference between this legacy and 4.2 secure is how they do a key exchange in the pairing process. So it was pretty quickly identified that there was a deficiency in the key exchange. If somebody observes this key exchange in the legacy version, they're able to break the future encryption between the devices. And so in 4.2 secure, they fix this by switching to an elliptic curve Diffie-Hellman key exchange. Since this device that we're looking at and a lot of other devices support this legacy mode, that's what we're going to be talking about mostly here. So looking at this pairing method, it starts off with a pre-connection phase. This is where a device is going to beacon out and say, hey, I'm a device that you can connect to. Assuming that that user wants to connect to that, you move on to phase 1, which is where a feature discovery and an exchange of capabilities is going to take place. This is how they determine what security modes they're going to use. And in phase 2, they start trading keys, and this is where the encryption begins. And then in phase 3 is where the devices become bonded together and that pairing process completes and becomes permanent. So starting with the pre-connection phase, you have a peripheral device, in this case our safe. It's going to be beaconing out an advertisement. A phone is going to receive this advertisement and it'll pop up in the app and say, hey, do you want to connect to me? The user selects that they want to connect, and it starts with this connection request. Moving on to phase 1, these devices have now completed this initial connection, and this is when they're going to start talking about what security modes they're going to use in the future, and specifically what association mode is going to be used for the temporary key. So an important note here is that the actual device capabilities and what's actually being advertised might differ. So a lot of hardware supports more secure or later versions of Bluetooth than they're actually going to be using during this pairing phase. So getting to these association modes, they determine how this key, this temporary key, is going to be generated. The temporary key is a 128-bit value. Depending on the association mode, it doesn't necessarily come up with all 128 bits. So if that's the case, it'll be padded to 128 bits with nulls. And these association modes include just works, out of band, and passkey. Starting with just works, it uses the same key as Kanye's iPhone, which is just all zeros. It's the most basic connection mechanism, acting as a fallback for other devices. It doesn't have any hardware, additional hardware overhead. If you're following some tutorial online, there's a very good chance that it's going to be using the just works mechanism. It's commonly used in things like speakers and headphones and other cheap sort of devices. Next, we have out of band, which is where we're going to distribute this temporary key out of band. So it's not going to be in the Bluetooth channel. So this is commonly seen in like headphones using NFC, or in the case of this Apple Watch, it has kind of a swirling mass of dots. You hold your iPhone above it, and it captures the motion of this, and that's how it transmits the key. It's the most secure option available to you, but it does have the hardware requirements, either the NFC or a camera or a screen, something of that nature. Last one we'll talk about here is the passkey. This is where one device generates a key and a user has to actually input that into another device. It requires one device to have a screen and another to have an input mechanism. I've commonly seen this used in things like car infotainment systems. So now we have this temporary key. We're going to use this to form the encryption if this link is going to be encrypted. And we use it to generate this short-term key. The short-term key is going to be used to actually encrypt the future communications going into phase 3. Now, if an attacker listens in on this key exchange in legacy mode, since all of these values in the equations are known, they can break the future encryption algorithms. So in phase 3, we perform a long-term key distribution. So there's a few keys involved here. Some of them are exchanged to help devices recognize the devices over a long period of time. So one of the things that devices do, or they can do, is they can change their physical MAC address over time to help prevent tracking, and so some of these help resolve that over time. And at the end of this, the devices are bonded, which means that the future connections don't necessarily need to go through this full pairing process again. So there are some built-in mitigations to what we've talked about previously in Bluetooth. So for eavesdropping, there's link layer encryption using AES 128-bit encryption. And then in 4.2 secure and later, they switched this Diffie-Hellman key exchange, which gives protection against man-in-the-middle and eavesdropping. They also add this other association mode called numeric comparison, where you have two devices with screens and they each display a number, and a user has to verify the authenticity of each device. And then it provides that tracking protection by allowing the device to change its physical address over time. So mitigations are great, but just because the features are available doesn't mean that they're necessarily going to be used. Again, if you follow some demos or examples online, oftentimes they don't pay any attention to any of these steps. And the security of the encrypted channel relies on the confidentiality of the key exchange, for the legacy mode especially. And the association modes that are the easiest to exploit are also the simplest to implement and have the lowest hardware requirements. So as you start looking at some of the claims that these devices make, like this safe, it claims to use 256-bit AES and bank level encryption. So these aren't supported at the protocol layer. An application layer, you can implement whatever schemes you want. However, doing something like this takes more processing power and would decrease battery life. It also adds complexity, and so really, they're not going to do this. So, big red flag for us. So, looking at finding the vulnerabilities that exist in the safe. We start out like we often do with product security reviews, and we start looking at the documentation for the device. We start learning how people use it, how the developers use it, and how users use it. We do open source research. We want to see if anyone has hacked the thing previously. And we want to evaluate the attack surface. So we look at things like the input-output for the device and what communications channels it uses. If the device is more or less a black box, meaning it doesn't have many of these things available to us, or in this case our safe, uh, a good first step is going to be to analyze the communications that it uses under normal operation. So in normal operation, we have our safe. It's going to beacon out its advertisement. A user is going to be using the app, in this case the Android app. They'll see the safes pop up in the app, and they can choose to pair with it. Assuming they choose to pair with it, they are brought to the screen where it wants a PIN code. And the PIN code here would be the same numeric PIN code that a user would type in on the top of the safe to get it to open. And it should be noted that the pairing in that step is actually separate than the Bluetooth pairing. That's already happened at this point. And this is an application level pairing that happens. Assuming the user puts in the correct PIN code, then they're presented with another screen that allows them to initiate commands on the safe, like open it or change the lighting, various other things. So back to this application. So like we said, the safe's just beaconing out, hey, connect to me. Assuming a user wants to connect to it, they're able to. So this allows anyone near the safe to attempt to connect to it and enter this PIN code. So right away, that's a bad sign. But in doing this process, we realized that the application doesn't have any penalties for incorrect PIN code entries. So that allows you to do something pretty quickly, like our lousy attempt here, just brute forcing the key. Since it doesn't penalize you in any way for getting it wrong, you can quickly exhaust the key space for entry into the safe. Since it only supports 4 to 8 digit PIN codes with numbers 1 through 5 available, we just wrote this Python script and instrumented the application over ADB, and we're able to log into the safe. Now, this is a vulnerability, but this isn't what we wanted to find. This isn't good enough. So where do we go from here? Well, we don't have too much else to look at this point. So we're going to look at this network communication. So let's look at the Bluetooth level. So we're going to try to capture a user pairing with and opening the safe. So I'm going to hand it over to Dan here to talk more about this Bluetooth capture process. Thank you.
All right. So the next phase, we want to, like Austin said, capture the communication between the application and the safe. So how do we do that? So we use this device called the Ubertooth 1. It is a USB dongle that can be used to monitor Bluetooth and perform analysis on the capture. The capture can be imported into Wireshark. And the device is relatively cheap and has good documentation online. It's also an open source platform, so those are the reasons why we liked it. There's a link for that there, hopefully if you can see that. So what we did was we took a capture of just playing around with the safe. We opened up the application, we connected to the safe, sent it a few commands, right? Unlocked it, dimmed the LEDs a little bit, just messing around. So the next step is we take this capture that we just did, right, that contains these various actions that we took, and we open it up in Wireshark. Immediately what we can see is that the capture is unencrypted, or the communication is unencrypted. The write commands that the application is sending to the safe are in the clear. You can see the payload there. Just taking a look at it briefly, there are some interesting data sequences that are being exchanged, but at this point, we really don't understand the application protocol. So just an example of encrypted versus unencrypted. The image at the top is just an encrypted capture. So what we see is like an encryption request, and then afterwards it's just layer 2 fragments that we can't decrypt. And then the unencrypted traffic, right? We can basically see everything that's going on. So that was actually just like a quick and easy, win. Uh, so in the case where there is encryption, you can still deal with that based off what Austin said, right? The issue with the pairing exchange. Um, so a nice tool to use is Crackle. This will perform the brute force attack on that vulnerability, and you will be able to brute force the temporary key using this tool alongside the Ubertooth. So at this point, we have a few options that we can take. We can, continue with the Bluetooth captures. Um, Take a look at the Android APK or iOS application. Another option is just to take the firmware off the device, right, and analyze that instead. So, the step that we took was just taking a look at the Android APK. And this was because sometimes these APKs are relatively easy to understand and reverse engineer. We can decompile the APK, and hopefully it doesn't use obfuscation, right? Even if there is obfuscation, there are ways to deal with that, but just hope for the best. So it ended up actually that the APK wasn't obfuscated too heavily, but the tools that we used to analyze it. So first off, we download the APK from an APK archive website. There are various of these around. One example that we used was APK Mirror. So it just allows you to download APKs without a phone. You can also grab archived versions, historical versions. So once we get this APK, we run APK tool and dex to jar on it. This gives us the Java classes back, and then we open those up in a decompiler. So we used Loiton, which was a GUI for the Procyon decompiler. There are other ones out there, but just what we used. So opening up the APK, first we want to just take a look at what's inside. Take a look at the hierarchy as well as the class names. See if anything pops up, and then look for points of interest inside those classes. So things that we're looking for are just communication between services, any type of hard-coded definitions, hard-coded constants, interesting strings, that might have to do with the safe. Just anything to interact with the safe in general. So the first point of interest we found was in the order utils VT20 class. We found various commands in there with constant definitions, and these seem to be the application layer commands that the APK is using to communicate with the device. And there are a few in there. There's like command author, command info, command finger, door, right? So that kind of sounds like it has something to do with opening the safe. We weren't sure about what some of the other ones meant, but at this point, we just want to see if these are inside the capture. So unfortunately, we didn't immediately see these magic constants in the capture, but we do know that our Bluetooth capture, right, contains these commands somehow, because we did interact with the safe, we did unlock the safe, we did mess around with the LEDs, so they should be in there in some form. So we must be missing something. So the next step is we have to go back into the APK, see what they're doing with those commands, and it ends up it's being transformed. There's some type of encoding and packing function that's being applied before they are being transmitted. So that's why we couldn't see them directly in the capture. So fortunately for us, this packing algorithm is easy to understand. What they do is they take the command payload, they divide it into 20-byte chunks, and then bytes in these chunks are then split off by each nibble is split off, added to 97, and then stored as its own byte. So you transform like 1 byte into 2. There's an image on the bottom that shows this. The image on the top is just the function that performs this. So we don't really know why they did this, but they just do it. It's relatively simple to reverse. Image to the left just shows us joining those bytes back together, and script to do that. So at this point, we want to apply our decoding to the actual capture and just see what commands are being sent. So we do that, and we see a couple of commands. And then here, this image shows the timing diagram of the commands. So we see, it's doing this like pair command. And keep in mind, this is the application pairing command, so not the same as Bluetooth pairing. But it's setting some type of pair command, get author, setting the time, opening the door, opening the safe perhaps, and then a bunch of other commands. Initially, some of them were not that interesting. We kind of glanced over them, like get author. But it ended up this command was actually pretty essential, and we can talk about that in the next slide. So again, we initially thought this command stood for get author of like the app, get author of some type of write request. But it actually stands for get authorization. So what you use this command for is use it to request an authorization token. And in the structure of this command, you actually send it with the pin code to the safe. So there's a field in there, if you see the image, that's reserved for that pin code. So immediately here, there's an issue because someone who's eavesdropping can see this command being sent. The pin code is in there, right? So they can extract the pin code and identify what that is for the device. So what the authorization request responds with is the safe will give you back a 4-byte authorization token. Using this token, you can then issue privileged commands. So a sample of a privileged command is just opening up the safe, right? So below there's an example of that where you take the 4-byte authorization token, you place it in the first 4 bytes of the open command. You send that, right, and then it lets you open it up. So it ends up, if all you want to do is just connect to the safe and open it up, the bare minimum that you need to do, right, is just to request authorization and then get that auth token and then send the open command with the auth token, right? So some of the other commands that we saw before were not really necessary for that task. So at this point, we understand this application layer protocol a little bit better. What we want to do is we want to play around with it a little bit, modify some payloads, see what happens. So at this point, we're not using the app anymore to communicate with the device. We're using our laptops. And we chose to use this Node.js Bluetooth library called Noble, and mainly just due to cross-platform support. So using this library, we just mess around with the safe. And also we use a tool called Packet Logger on Mac. It's just a neat Mac tool for sniffing, for examining Bluetooth traffic. So what we did is we test around with the safe. We issue some unlock commands. We want to make sure that we're not hitting some type of cached or pre-authorized behavior. So we change the pin code, right? Rerun it, see what happens. And the safe opened. So it was, this was very surprising to us. So, at first we didn't, we thought we made a mistake or something, right? But it ends up that the safe actually doesn't check the PIN code of the get authorization request. It just ends up always responding with an authorization token, even if you give it the wrong PIN code. So that's pretty bad, right? That's that's like this image, right, where you have this absolute failure for security, where you have this locked door, but we can just kind of ignore it and go around. So what this ends up meaning is that any attacker can open this device by just issuing 2 commands, right? And we also verified this by purchasing a brand new device off Amazon, and right out of the box, right, worked. So the results, I guess, these safes, right, they're constantly broadcasting advertisements. Anyone can connect to them. And then, during normal operation, when a user, right, tries to open the door, it transmits the PIN code into clear. So that's a big issue too. And then, the really bad one where anyone can kind of connect to these devices, request an authorization code with any PIN value, right? Get that authorization token back, and then use that to unlock the device. You can also do other cool stuff, right? Like dim the LEDs if you want. And there's also no remote update mechanism that we are aware of. So this should work quite reliably with any device in the series. So here's a demo video of this. Hopefully it plays. So at this step, we're just showing the PIN code is set to 54321. We're running this unlock command, unlock script. It's waiting for that advertisement for the safe. Once it gets that, it's going to issue that authorization request, get back that authorization token, and open it. And now we change the password just to show that you don't even need to know the password to open it. So we change it to 12345. We're going to run the exact same script, and it's going to do the same process, right? It's just going to wait for that advertisement. So here it's scanning. It's going to wait for that advertisement. Once it hits that advertisement, it's going to issue that authorization request, get the authorization token back, and then unlock it, right? So same process, doesn't matter. All right, with that, I'm going to hand it back to Austin for the next part.
All right, so we've seen several failures that have been made in the design of this product. So let's talk about some good practices for your products. So some really simple things you can do, or that would have helped here, would be something like even hiding the manufacturer name string in the Bluetooth advertisement. So as it is here, all of these safes are beaconing out, hey, I'm a Vault-X safe. And now we know that all of these Vault-X safes are vulnerable. So if we ever see one of these advertisements, we can just open it. So you can imagine driving down a street or something and just popping all of these open. So if that wasn't broadcast out in the open, then we would at least have to do some kind of work to figure out if this device was one of these safes. You want to use software application obfuscation. So again, this Android application, we were just basically able to decompile and get back readable source. Something as simple as ProGuard or something else would have made it that much harder to get to that point. And that's really what you want to do, is make my job as an attacker harder. So this isn't a guarantee of security, but it just raises that bar that much higher. And something that would have really helped here would have been implementing a pairing enable switch on the device. So just allowing any user to pair to the safe at any time is probably a pretty bad idea. So if there was a key press sequence or an actual button on the safe that you had to hit to initiate this pairing, at least the first time, then that would at least require some kind of physical access to the device. And you want to use the most secure Bluetooth version and association modes available to you. So you want to use out of band if you can. It's the most secure. You want to use Bluetooth 4.2 secure mode and later with that Diffie Hellman key exchange. And possibly most importantly, you can't think like these manufacturers. Uh, you can't think that they can't break your encryption if you don't use any encryption. You have to use that link layer encryption that the protocol allows you to. So some other general tips. Um, you want to keep all of the data that is sensitive encrypted. So even beyond the link level, if they had taken that PIN code in that get authorization field and maybe entangled it with some other user-defined secret, then it wouldn't have even mattered if we could have, captured it. You want to assume scenarios where you have a full physical compromise of the product. So assume that somebody's going to be tearing apart your product, pulling off the firmware. Assume that we're going to be taking your application and reverse engineering it, because we are. And you want to really keep in mind that the more avenues and communication pathways and things that you add to your applications, that's just broadening the attack surface. So it's making my job as an attacker easier. The more things you add, the harder it is to secure. In the case here, you want to use really strong credential policies. So having that really short key space and having the really small key space allows an attacker to brute force the PIN code in this case. And if you are going to use credential policies, don't give a user an unlimited number of retries to get it right. Give them some kind of timeout, something like that. And you really need to understand the security implications of subcontracting out development. So in this case, when we started looking at the software application, it became apparent to us that it was a Chinese company that developed the application, and they primarily do IoT subcontracting for various vendors. And that's pretty common, right? Not everyone has the in-house talent or resources necessary to build a product from end to end. And so it's pretty common to subcontract out various pieces of the development. But you want to keep in mind that some of these subcontractors don't necessarily have the same security model that you might. So you need a way to really verify that they're implementing their pieces in a secure manner. So some other things you can do for prevention and remediation. So like Dan said, there's not really a remote firmware update mechanism for this. You don't want to be caught in the scenario like this company where you have to put on your website that they're offering an upgrade if you mail your safe back to them. So having a user have to physically send the device back is probably pretty bad. Some simple things you can do, you can run a bug bounty program. So give out a small cash award to various parties when they find bugs in your product. That helps increase the scope and talent pool that you have looking at your product. And usually those are parties that will sign NDAs and various other things to protect your secrets. You can also engage in professional security audits. It's something that my company does. We take a look at your product under NDA, we analyze it, and we come up with any possible ways we can find to break into it, and we help you to secure these issues going forward. And you want to keep an open communication pipeline, and that's with both the security community and with your consumers. So if you do have an issue or a bug that comes up, don't deny it, be open about it, and you want to be as open as possible. The easiest thing you can really do here, though, is start a responsible disclosure program. And that can be as simple as having security@yourdomain.com and just receiving disclosures when a researcher finds your vulnerability. So that's really all we have here. Here are our email addresses. You can feel free to contact us if you want to talk about product security or embedded system security, or if you want to hear more about the safe. We also have a blog post written up about this safe that you can check out. The address is also here.